Section 5.3 is about angle bisectors in a triangle. Let's first remember what an angle bisector is. An angle bisector is a ray that divides an angle into two congruent adjacent angles. Remember, adjacent means that they are sitting next to each other, sharing a vertex. Another thing we need to remember is about the distance from a point to a line. The distance from a point to a line is the length of the perpendicular segment from the point to the line. So, in the diagram, ray PS, right here, is the bisector of angle QPR, and the distance from S to PQ, so this distance right here to PQ, so from S to PQ is the measure of SQ. So again, the distance from S to PQ is this length right here, SQ, where segment SQ is perpendicular to ray PQ. So in order for us to find the distance between S and the ray PQ, we have to find the perpendicular distance. So SQ would be perpendicular to PQ. And the distance from S to ray PR, so from S to ray PR, is the measure of SR, so this length right here, where segment SR is perpendicular to ray PR. So again, to find the distance from a point to a line or to a ray or to another segment, it has to be the perpendicular distance. And that brings us to our next two theorems, Theorem 5.5 and Theorem 5.6. The first is the angle bisector theorem. The angle bisector theorem states if a point is on the bisector of an angle, so you can see here we have ray AD that is bisecting this angle into two congruent angles, and point D that is on the bisector, then it is equidistant, remember equal distance, from the two sides of the angle. So any point on the angle bisector of an angle is equidistant to the sides of the angle. So any point along here, if I were to find the perpendicular distance from that point to each side of the angle, it is equidistant to each other. So again, if ray AD bisects angle BAC, so here's ray AD bisecting angle BAC, and DB is perpendicular to AB, and DC is perpendicular to AC, because again, the distance from a point to a line has to be perpendicular. So again, when we have a point on the angle bisector, then DB would be congruent to DC, and that would be true for any point on that angle bisector. Next, we have Theorem 5.6, the converse of the angle bisector theorem. If a point is on the interior of an angle, so it's just on the inside of the angle, and is equidistant from the sides of the angle, then it lies on the bisector of the angle. So here again, we have point D that is on the inside of angle BAC, and DB is perpendicular to AB, and DC is perpendicular to AC, and we also know that DB and DC are congruent. It is marked with tick marks right there. Then that means that ray AD is the angle bisector of this angle. So when you can see that some point in here is equidistant to the sides of the angle, then you know that point lies on the angle bisector of that angle. Here's our first example. Number 1, find the measure of angle BAD. So here's BAD right here. So we see we have an angle BAC and a point D on this ray right here. At this point, we are unsure if this is the angle bisector of angle BAC. So we notice that from D to AC, it is perpendicular, and from D to AB, it is perpendicular. We also notice that the length here is 18 and the length here is 18. So if these two sides are congruent, that means that ray AD must be the angle bisector of angle BAC. So point D is equidistant to the sides of the angle, so therefore ray AD must be the angle bisector. So again, since point D is equidistant to each side of the angle, and those lengths are perpendicular to each side of the angle, then it must lie on the angle bisector. This is according to the converse of the angle bisector theorem. So therefore, angle DAC would be congruent to angle DAB. So if this angle is 54 degrees, then that angle is 54 degrees. So the measure of angle BAD, like we're asked to find, would be 54 degrees, according, again, to the converse of the angle bisector theorem. Example number 2, for what value of x does P lie on the bisector of angle A? So if P would lie on the bisector of angle A, that would mean that the distance from P to B and the distance from P to C would have to be congruent according to the angle bisector theorem. So x plus 8 would have to equal 3x minus 6. If those two lengths were equal, then we could conclude that ray AP would be the angle bisector of angle A. So first thing I would do is subtract x. So I have 8 equals 2x minus 6. Add 6 to both sides, so I have 14 equals 2x. Divide both sides by 2. So I get x equals 7. If x were equal to 7, then point P would lie on the bisector of angle A. Example number 3. Do you have enough information to conclude that ray QS, this ray right here, bisects angle PQR? So notice here that it is equidistant. Point S is equidistant to the sides of the angle. However, we do not know if this is the perpendicular distance. In order for us to conclude that ray QS is the bisector of angle PQR, we need to know that point S is equidistant to the sides of the angle, but we also need to know that those segments are perpendicular. So no, I do not have enough information. So no, we only know that SP is equal to SR, but we are not told that those segments are perpendicular to the sides of the angle. If we were told that they were perpendicular, then we could conclude that ray QS is the bisector of angle PQR. Now on to another theorem, 5.7, the concurrency of angle bisectors of a triangle. So this is a lot like the concurrency of the perpendicular bisectors of a triangle that we looked at in the last section. This theorem states the angle bisectors of a triangle intersect at a point that is equidistant from the sides of the angle. So again, I like this because it is color-coded. So AP, BP, and CP are all the angle bisectors of the three angles in the triangle. So we would know that all of these angles would be congruent to each other. Okay, and then if we know that we have all those angle bisectors, the segments in blue, so we have PD, PE, and PF, all of those would be equidistant to the side. So all of those segments are congruent. So last time we had perpendicular bisectors and we knew where those intersected, they were equidistant to the vertices of the angles of the triangle. But in this one, we have the angle bisectors that are all equidistant to the sides of the triangle. That point of concurrency of the three angle bisectors of a triangle is called the incenter. The incenter always lies inside the triangle. I always just think in center, inside. I would write that down in my notes. In center, inside. The incenter P is equidistant from the three sides of the triangle. So P is the center of a circle that will touch the three sides. So again, the incenter would be like the center of a circle, and it is equidistant to the sides of the triangle. So therefore, those distances would be like the radius of a circle inside of here. So last time we had one that was circumscribed outside of the triangle. Now we have a circle inside the triangle. That is called inscribed. So again, the circle that is encompassing all of those equidistant lengths to the sides of the triangle is called inscribed within the triangle. So the incenter is inside, and that circle that is touching all of those equidistant segments is inscribed within the triangle. So let's look at example number 4. In the diagram, G is the incenter of triangle RST. So that means that all of these segments going to the vertices of the triangle are the angle bisectors of the triangle. Now they want us to find the length of GW, and the hint is to use the Pythagorean theorem. Now, if G is the incenter of the triangle, that means that from G to the sides of the triangle are all congruent. So let's mark that in our diagram. So GV would be congruent to GW, which would be congruent to GU. So it said to use Pythagorean theorem. So if we look at this right triangle right here, since we know this is a right angle, since this is a right angle, I have that right triangle. So here's my right triangle, pulling it out here. I have G, U, and T. I know that this is a right angle, and I know that this length is 12, and this length is 13. And I want to find this length right here, x, since GU is equal to GW. So again, the Pythagorean theorem states that the legs squared is equal to the hypotenuse squared. So I would take x squared plus 12 squared equals 13 squared. So to simplify, I have x squared plus 144 equals 169. If I subtract 144 from both sides, I get x squared is 25. To undo a square, I square root, and the square root of 25 is 5. So if GU equals 5 and GU is equal to GW, that would mean that GW is equal to 5. And that would be my final answer. And that's it for this section. Make sure you jot down anything you don't understand that we can cover in class before we move on, and we'll see you then.